This video goes through the proofs when two chords of a circle intersect. The product of the lengths of the intervals on one chord equals the product of the lengths of the intervals on the other chord, and also its converse. Now for the converse, refer to Extended Response 2 on page 339 of your Cambridge textbook. So what we're trying to do, if we look at these two diagrams here, AB and CD are two chords of a circle that cut at P. Prove that at PA times PB equals PC times PD. Okay, so we're going to look at two cases, one where the intersection point is inside the circle, so case 1, and one where the intersection point is outside the circle, which is case 2. So for the first case, we can start by saying that this angle here has to equal that angle there because they're vertically opposite. So angle APC equals angle BPD because they're vertically opposite. And I suppose I could have just used the code. Anyway, also we know that this angle here has to equal that angle there because of the alternate angles in the same segment, sorry. So angle CAB equals angle BDP. So the code, our butterfly, or written in full, angles in same segment. It's abbreviated. So what do we know now? Well, we know that the other angles have to be equal. We could have known that anyway because of the angles in the same segment, but anyway, angle ACP equals angle BDP, angle sum of a triangle. Well, they're also the angle in the same segment, whichever way you want to go. So therefore, triangle APC is similar to triangle BDP. And the reason is we have 3 equal angles. Okay, so we're looking at similar triangles. So if you don't remember that, go back and review it. I've provided a video on similar triangles. Now, because we do have similar triangles, the ratios of the sides are in the same proportion. So PA over PD has to equal PC over PB. And the reason is corresponding sides of similar triangles are in the same ratio. So rearranging that, we have PA times PB has to equal PC times PD, which is what we were trying to prove. For case 2, where P is the intersection is outside the circle, and we can already see it marked, but angle BAD has to equal angle BCD. So you can see that slightly there. And that's the butterfly. Angles in the same segment. Okay. We know that this angle here is common to both triangles because what we're trying to look at here, probably should have explained that in the beginning. We're going to look at this triangle here and this triangle here. And we're going to prove that they're similar because we want them to be in the same ratio. Okay, so angle P is common. So angle APC is common to both triangles. So therefore, the third angle, ADP, has to equal angle PBC because of angle sum of a triangle. Now I'm going to label that on there so you can see which angles we're talking about. So that one in the green triangle and that one in the blue triangle, because you have to get those ratios right. And then we know this angle here is common. Okay, so therefore triangle APD is similar to triangle CBP because they have 3 equal angles. So now looking at your ratios, now be careful here. You really need to see those 2 triangles. And if you need to, draw the 2 triangles in the same orientation so you can see this. So PA, the long side of the blue triangle, over PC, which is the long side of the green triangle, has to equal PD, which is the shorter side of the blue triangle, over PB, which is the shorter side of your green triangle. And the reason being corresponding sides of similar triangles are in the same ratio. So rearranging that, you'll have PA times PB equals PC times PD. And we are done. Oh, and a code, if you're using this for something else, if you didn't want to write it out in full, again, different textbooks vary on whether they use codes or not. Jacaranda uses codes, Cambridge doesn't use codes, Pearson doesn't use codes, but the code is that there.